All right, everyone. Thanks for joining. Here is another webinar, another Tensorleap webinar. I'm Yotam Azriel, co-founder and CEO. Tensorleap is we are expert in explainability and applied explainability about how to debug and explain neural networks. Today, we have a really cool talk about something that most of us don't usually think about. Usually we are building AI models to make some structure in billions of samples in unstructured data like video and models. And Eliahu here came up with another idea, another huge bank of data that is unstructured, and here to talk about what we can learn from the model themselves. So today, in different hubs, we have millions of models from vision to NLP that encoded a bunch of information. Eliyahu is an expert and built very interesting techniques on how we can learn from those model weights themselves. And it's going to introduce a new model atlas, a way to make those structure and to expose the information that they've been learned. Eliyahu is a Google PhD fellow and PhD candidate in the Hebrew University. Eliyahu, thank you so much for joining us today, and the stage is yours.
Thanks. Thanks for your time and thanks for inviting me. So yeah, today I'm going to speak about my PhD work, which is basically what can we learn from a million models. And just as a spoiler, what we're seeing here is not a galaxy, but it's actually about 200,000 models from Hugging Face. And throughout the talk, we're going to parse this type of atlas and understand how to construct it, what can we do with it, and why is it even interesting. So the whole motivation for this work, this line of works, is that nowadays we have millions of publicly available models. And in order to actually navigate them, what we came up with what our idea is that we need to chart what we call a model atlas. So let's start by defining what this model atlas is. We'll define it as a directed acyclic graph where each node is a model and each directed edge, so these edges have an arrow here, is a weight transformation from one model to another. You can think of this weight transformation as either checkpoints throughout training, but also fine-tuning, quantizations, model merging, etc. And then we'll have edge features, which describe the transformation. So for each edge, we can attach things like the type of optimization, the samples themselves, what the batch size is, and all of the hyperparameters. And we'll have node features, which I like to divide into traits and metadata. Traits are functional attributes, things like the accuracy or robustness of the model, and in general, everything the model has learned, maybe the interpretability of the model, stuff like that. The metadata are descriptive properties, things like the creation time, the license, number of downloads, etc. And in order to visualize large model populations like we did in the beginning in that galaxy visualization, we can use colors to color the nodes and edges according to different features. And we can use node sizes. So we can change the size according to another property. And another very important attribute of this atlas for our talk is that the special location has no meaning. So if you look at these two atlases, they're exactly identical. So it's not like a clustering of something like that. And the reason is that these atlases, when they're large, they're highly non-planar. And if we want to visualize them in 2D, we need to project them somehow. And to do that, we use a graph layout algorithm, which tries to minimize edge crossing. But as you can see, these two types of things are identical. So the location has no semantic meaning. And this type of model atlas actually enables a variety of tasks, which we'll go over some of them, but one of them is what we call meta-ML research. Another one is model discovery, model forensics, and many more things. So let's start with meta-ML research. And the idea here, this is a term we came up with, which is sort of the sociology of AI communities, of the entire ML community as a whole, and to try and understand trends and stuff like that. So let's look at this model atlas here, and try and slowly parse it and do like a small case study of what we mean by MetaML research. So if we look here, we have about 200,000 models from Hugging Face again. And of course, each node here in this graph is a model. Each edge is a weight transformation. The colors represent the type of weight transformation. So these cyan ones, adapters, are things like LoRa. Uh, Greens are full fine tunings. Merges are taking two or more models, their weights, and doing some weight averaging, and maybe to fuse two different tasks they know how to solve and improve their capabilities or fuse them and stuff like that. And we have quantization, roots, and stuff like that. And the node size encodes the number of monthly downloads. And we can see we have very popular models. Some of them have over 10 million monthly downloads. And these models are taken from Hugging Face. And then because, as I said before, spatial location has no meaning, and in order to kind of parse this large model collection and try and understand things about it, I also divided it into different parts according to the community. So all the models here on the top are computer vision models. On the bottom, we have NLP models. On the left here, we have VLMs, vision language models. On the right, we have some audio models, and we even have a small cluster of robotics. These are VLAs, vision language action models. And immediately, and also just for your convenience, I also annotated some of these models, like popular models, so you can maybe spot some you know who they are. And immediately we can see very different structures between the communities. For example, we can see that the actual structure or connectedness of the different communities is different. But perhaps the most striking difference is model merges. We can see that the NLP community has widely adopted this technology of model merging, while other communities hardly do it. There are a few in VLMs, a few computer vision models, but hardly ever. And we don't yet have the answers as to why this is and what is so meaningful about model merging. But it's definitely one thing we want to kind of use this model atlas as a resource to surface these things and hopefully understand them and maybe transfer the knowledge. Maybe other communities should also start looking into them and doing these things. Um, Another thing we can do with the model atlas is track and trace emerging trends and throughout time, and hopefully in the future adapt them early on. So if we look here at markers 1 throughout 5, marker 1 is stable diffusion 1.4, marker 2 is stable diffusion 1.5, marker 3 is stable diffusion 4, 4 is stable diffusion XL, and 5 is flux. And we can actually trace the adaptation of the community of LoRa fine-tuning. LoRa is this parameter efficient fine-tuning method. And we can see that early on, it was hardly any reds. And at the end, almost exclusively, the community is using fine-tuning, LoRa fine-tuning. And again, the idea is that hopefully in the future, we'll be able to identify new architectures, new optimizers, and new technologies in general, and spot them early on and start using them and not wait a long time. And also for other communities to use them. So we can see, for example, that the audio community hardly does any LoRa fine tuning. It hardly does model merging. It hardly does quantizations. And we want to kind of have the community use the model atlas as a resource to study these things and understand how to accelerate ML research as a whole. Another very useful thing of the model atlas is actually model discovery. So the idea here is fairly simple. We all know that training is expensive, time-consuming, bad for the environment, etc. And we also know that in large model populations, things like Hugging Face, there are many models that exist and can solve many of our downstream tasks. And indeed, in one of our recent papers, we actually verified it by looking at different model families. These are every connected component here is a set of models that are fine-tuned from one foundation model. So here on the right, these are Llama models, and on the left, these are Quen models. And what we actually found is that while the popular models are very popular and everybody downloads them, they're actually very, very good models, which are, we call them hidden gems, which nobody knows about, but outperform the popular models by a wide margin on many different tasks. So for example, math or coding and stuff like that. And what this actually shows is that we can find specialized models for individual use cases that are very good and maybe people don't know about and will need to kind of do model discovery at scale. But then comes the question, if we already have this atlas, right? I just showed you two examples of atlases. Why did I claim in the beginning we need to chart it? Why do we actually need it? And the answer is that we don't really have the model atlas. So in practice, what the documentation for most of the models is missing. And what we have is this partial and fragmented viewpoint of the models. So where we're actually at is more something like this, where the space is very dense with many, many models, which nobody really knows about. But some of them are very, very good, like the ones I just showed you in those hidden gems. And we need to discover them. And indeed, when looking at Hugging Face, we did like a case study on Hugging Face. We see that over 60% of the models on Hugging Face have no documentation at all. And even the remaining ones are very sparsely documented. So for example, from the remaining ones, only 13.4 carry information about their performance, or they're only 30% about their base model. And what this causes is the situation where most of the models are lost and effectively unusable, which prevents all of these useful use cases I just described. So the whole point of my PhD and our whole position is that we actually need a semantic embedding space for models. Similar to how we train embedding models for text or for images, we need an embedding model for models themselves, which will take us from this current fragmented and partial view of the model universe, of the model population, to this full model atlas, which we can use for all of the useful use cases I just described. But then comes the question, how can we actually learn from a million models? So I showed you what can we do with a million models, ideally, potentially, in theory, but how can we actually learn? And the answer is that actually models themselves or their weights are a data modality. So we can treat the models themselves as data points. Each model is a data point, and then do things similar to how we do things with images and text, but just with models themselves now. And here comes this idea of weight-based learning. This paradigm of weight-based learning, or field of weight-based learning, um, follows the following premise. So when we optimize a model, when we train a model, what we do is we take the architecture of the model, the objective, the data, and the initialization of the model, all these hyperparameters, we optimize them, and we end up with a trained model, and specifically the weights of the trained model. And what's important is that these weights actually contain and encapsulate all of this information about the hyperparameters, the data, all of the priors we introduce, and it's all in the weights. Maybe not all of it because there's some compression, but nothing that the model can do is not in the weights. And then the idea of weights-based learning is that what people usually do is they upload it to some model repository. This can be Hugging Face, but it can also be just your cluster at your company or your institution, your research institution, whatever it is. You upload it to somewhere or put it somewhere. And then what weight-based learning tries to do is basically to train meta networks. These are specialized neural networks, which take the weights of other neural networks as input, basically constructing a data set of models where each sample is now a model, trains a neural network on these models in order to perform tasks of completing information of the model atlas, basically recovering all the missing information of the model atlas. So our meta network will try and learn some representation, semantic representation of the models themselves in order to uncover things like the atlas structure, predicting node attributes, edge attributes, etc. And the problem with weight-based learning is it's very challenging, mainly for two main reasons. So first of all, weights are extremely high dimensional. So if we take a standard sample and image data set, that's about 150,000 parameters for a single image. If we take even a small neural network like a Resonant 50, it's 25 million parameters, stable diffusion is 700 million, LLMs are billions to trillions of parameters. So now each sample is orders of magnitude larger. But what's even worse is that neural networks and their parameters contain many symmetries, which we need to be equivariant for. And probably the worst one is permutation invariance. So the idea here is that if we take a neural network and we just permute the weights of the neural network, we permute the neurons, sorry, of the neural network in a corresponding manner between each two consecutive layers, we end up with the exact same function, but obviously the raw representation of the weights is vastly different. You can think of it a bit like working with point clouds or something like that. And then what we'll need to do is we'll need to design permutation equivariant architectures in order to process neural networks, which complicates the matter even more. So this is what the community actually does mostly, these permutation equivariant architectures. But the problem is it doesn't really scale. It's very hard to design these architectures and they don't really scale. And our idea, the idea of my research is that, wait, what if we can actually avoid this permutation symmetry altogether, these symmetries altogether, and find these hacks or weight space shortcuts or areas where we can avoid them and learn much easier. And indeed, this is what the set of works for my PhD does. So this is kind of a high-level overview of our works. So we have works on recovering the structure of the atlas. This is actually recovering this graph, recovering the edges. We have works on recovering weights. So basically actually recovering the actual weights of models which are unknown. We have works on recovering edge attributes, for example, recovering the number of training samples a model used, again, by using only the weights as inputs. And we have a few works on recovering node attributes, which we think is one of the most important things because this allows for model discovery and model search. So now let's start to dive a bit deeper into some of the works. So the first work is the spectral detuning. And the idea is the following. What we're trying to do is we're trying to recover weights of hidden models. And the idea is that public models are very useful, of course, but they're also risky. And what usually happens is that in the first stage, we train an unsafe model on web data, and then these models undergo safety and alignment training. And what the task we're proposing and then showing how to solve to some extent does is it assumes that we have a safe model, an aligned model. And what we want to do is we want to recover the weights of the initial unsafe model. And when we say the weights, it's important because we don't actually want to kind of do reversing alignment without the weights, because if we do that, we'll end up with something which only recovers some things for a small slice of the distribution. This is what current methods do. They kind of continue further fine-tune on a specific data set, and then they show the undo alignment. But what we want is to recover the actual original model. And what we do, our trick, our hack, is to actually think about the mathematical properties and the weight formation process of these models. And in some cases, we're actually able to revert it almost perfectly. So very quick background about our setting. What we assume, what happens, as I said, is that we first pre-train on general web scale data, and then we fine-tune on a specific task. And we can view it as following. Well, all these slides for this paper are looking at the perspective of a single model layer. So what we do is just apply it on all the layers independently. So W now is not a model, it's a single layer of the model. It doesn't matter which layer. So we have this W, which is we call it the pre-fine tuning, but this is a pre-trained layer of the model, which is K on D. It's a matrix, basically. And when we fine tune it, we end up with some other matrix with some other model in its matrix, W prime. But we can also look at this fine tuning as basically taking W and adding it to it some delta W, the update to the weights of the model, and we end up with W prime. And a nice observation or a problem that occurs is that fine-tuning large models is very costly. And for this, there was this observation that the actual weight change while fine-tuning is low rank. And then there was this paper, this great paper, which was proposed to try and accelerate it, which is called LoRa. The idea is that we can basically parameterize this delta W by a low rank matrix. We can approximate this delta W by a low rank matrix. And then if we reparameterize this low rank matrix into two smaller, one narrow and tall and one short and wide matrices, we'll have a low rank matrix which approximates the performance. And another nice property of LoRa is that if we merge the weights back into the original one, so if we now take B and A, these two matrices which were trained, we multiply them together to end up with M, a new matrix which is low rank. We call it, the rank is at most R here. And then we sum it up together. So now we do W plus M, we end up with delta W. And it doesn't incur any additional parameters because M is now just a linear operation of with W. And what all the current methods assume, or implicitly assume, is that recovering W and BA, or this M, from W prime is impossible, right? They assume that once you sum it, it's impossible to actually recover it. So let's show our problem definition. So what we formulate this problem is basically under the setting of LoRa, and assuming we have n LoRas, later I'll speak about the number of n, but it doesn't have to be very large, but assuming we have n LoRas, which were all fine-tuned from the same original model. And let's say we take llama and we fine-tune it n times with different LoRas. This is what the attacker sees. Under the hood, what we know, because all of them share the same pre-trained model, we know that W is shared between all of these n models, and each one has a residual of the LoRa residual, the BI and AI, which is different. And then the task of the attacker is that when given access only to this W1 to Wn, W prime 1 to W prime n, the attacker tries to approximate W, the pre-trained one. And so it tries by using W star. And if we speak a moment about intuition, the reason it's even possible is that because W is shared between all of these models, basically the only increase in parameters is dr plus rk times n. But we have dkn equations. So now it's an over specified system of linear equations, and we can actually solve it. And what we do, this is exactly what we do. So this is our loss here. There's no learning actually in our solution. It's sort of like EM. What we actually do is we need to solve a system equation. We need to find n+1 matrices, and we define this thing. And the very important thing is that because we know that these matrices are low rank, we can condition that while we optimize. We can constrain that, and this actually becomes very tractable and actually converges. And if we look at some results, I won't go over all the implementation details, but if we look over results, on the results, we can see that it actually works almost perfectly. So if we look at the left here, we took stable diffusion LoRa's from in the wild. We just downloaded them from the internet, and we see that the top row here is what happens if we just sample an image from that from one of these LoRa's. And then if we just take the mean of all of these LoRa's, this is one of our baselines, you would assume if the mean was zero mean, meaning all the LoRa's just sum up, average into zero, then the problem would be trivial. But we can see that it's not trivial. And then at the very bottom row, we see the ground truth. What happens if we take the original pre-trained model? And we see that our solution approximated almost perfectly. And in fact, the only difference I could find is this small tail which we added. And we do the same also with Mistral and LLM, and there we also do it for two stages. So we undo alignment fine-tuning as well. We undo SFT and then alignment fine-tuning, and we do it also almost perfectly. And in fact, if we look numerically, we achieve numerical stability. So like e to the minus 16 loss for this, L2 loss. Which actually means that any sort of model method that uses LoRa for fine-tuning is vulnerable to this pre-fine-tuning weight recovery attack. Okay, so that was the first paper about how to recover the weights. Let's quickly go over things related to model discovery. So this is a paper and model discovery is kind of a step towards model search. So our overarching task would be to find the most suitable model for a given task. And the input is just a set of models and a search query. So you can think of it, for example, you go to Hugging Face, you want the best model to perform I don't know, medical lung images and classification or segmentation. And the output would be the set of models that best match the user query, the search query, in order to perform that task. And an important thing is that we never assume any access to in-distribution data. Right? If we have access into distribution data, we can just evaluate the set of models and find the best one. But we never assume any access to it for two reasons. First of all, it's infeasible to actually evaluate all the models in the world or all the tasks and data sets. It will be infeasible to actually do it. And second of all, we don't really know what each model does, so we can't a priori, so we can't just evaluate it on something because we don't know even what modality sometimes it's working on. And in order to perform search, we need basically two main things. We need to do what each model does and how well it performs. I like to think of it as filter and sort. So if we go into Google, we have the search query which filters, and we get the best matching results sorted. And so we'll want to do the same thing. And what this first paper does is basically says that the trick here is to observe that the permutation symmetries, they only affect the actual parameter space, the neurons themselves, but not the function space. So if we look at the input and the output of the model, that is fixed. And then with that observation, we can basically do what we call probing. So what we do in this paper is our task is to predict the performance of a given classifier, again, with no access to in-distribution data. So we assume we have a set of input models. We assume that all of them were trained on some similar distribution of data, but we don't know their performance. And then we do a supervised learning task. And the idea here is basically we represent a model. Our representation of the model, the semantic representation, is the response of the model to a set of inputs. These inputs, we call them probes. So what we do is we take K probes, we optimize them and observe the responses, and then we feed in these responses into another small neural network, a predictor. It can be an MLP, a small attention model, like a small transformer or something like that. And we get some representation for our downstream task, in this case, regressing the performance of the model. And we optimize all of this end to end, and it actually yields very good results. And we're able to approximate the performance of models with a very high degree. Again, just based on the weight. So it's kind of magic, I think, where you can take the weights of the model and approximate with a high degree the performance of the model while never actually evaluating it in distribution data. And as I said, probing works very well, but probing a full model is very expensive, because if we think about it now, every batch of ours is a batch of models. And if we want to do a batch of, let's say, 1024 models, and all of them are 70 million parameters each, this batch is going to be huge. So the next question is, can we actually probe individual layers instead? We don't want to pass the probes through the entire network. Can we do it for individual layers? And the answer is that generally no, because the intermediate layers, again, exhibit the permutations. So we go back to this case where we have permutations. But here comes our next paper, which tries to tackle this. And what we actually our kind of hack or weight space symmetry avoidance hack is basically this idea that, or observation, that neuron ordering, the ordering of the permutations, is determined very early on in the optimization steps of the pre-training. And therefore, if we look at connected components of the atlas, these are these family trees or family connected components, we can probe individual layers, because then we have all the models within one connected component with fixed permutations. But then the question is, well, but then you'll have to train a bazillion different models, each one for different families. But actually what we found is that if we look at Hugging Face, it's enough to take 15 connected components, and they already account for over 41% of all the models on Hugging Face. So what this means is that Hugging Face is very concentrated. We have these huge, huge family trees, as we can see here, like Stable Diffusion or Llama or stuff like that, which have thousands or tens of thousands of descendants. And it's enough to train a small number of experts. So the task in this paper was to predict the model functionality. In particular, we get the model weights. We get a set of models. We have a set of models. Now we take weights of one of the models, the individual layers. So now it's not the entire model, but just a single weight matrix of the model. And we want to output the class or classes the model was trained on, classify them. And this is, of course, a step towards model search. Um, and as I said before, because we have no permutations, now we can learn a very simple meta network on individual layers. And indeed, we see that this is enough. So if we did kind of a small motivational experiment, and we see that if we work within trees, then our classification performance goes to almost 90%. This is a toy example with like binary classification. But if we do it between trees where we have permutations, then the accuracy drops to almost random. But we still need to handle the very high dimensionality of the weights. And for this, our architecture, which I won't go into, but our architecture, which we call probix, learns it learns probes, and simultaneously it also learns downsampling layers, which drastically reduce the dimensionality and make it tractable. Um, One last interesting thing about this Probix architecture is that in some cases we can actually align the representations we learned for a model with some other representations. For example, the clip text encodings. And what this enables us, this basically creates a shared weight language embedding space where we can actually query the weights with language and retrieve them, do things like with free text, ask for give me all the models for dogs, or give me all the models that know how to classify cats and stuff like that. And it actually works very well. So that was this. And again, I'm going to this kind of overall overview of the papers from my PhD. And we can sort of classify them into two types. One of them work directly on the weights, similar to what we saw in the first paper. And a different set of works do these probings, learning inputs for the model, looking at the stimuli, and learning a downstream model on the stimuli. But there are still many open challenges. So all the works I showed you kind of show the feasibility of this idea of weight-based learning on a model atlas, but we still have many open challenges. For example, designing weight priors. So unlike text or images where we know the priors, for example, in images, we know that spatial locality is very important. With weights, we don't actually know the priors. I think it's reminiscent of early days of computer vision where we try to still explore low-level tasks and low-level solutions and stuff like that. We need new architectures and methods. We need to scale it up. We need self-supervised and unsupervised methods. Most of the things I showed you were supervised training. And I think a very important thing, and something that is also relevant for Tensorleap, is the idea that we can analyze, we can add additional layers to the atlas. So I showed you some layers of functionality of the atlas, for example, performance or the fine-tuning type. But actually, this atlas is an open source tool, which we actually provide, which anyone can add their own findings. So if, for example, you're an interpretability researcher and you have a set of models, you can you can do your interpretability research or robustness research, get your results, and encode these results as node or edge features into the atlas. And then we'll hopefully be able to do the same kind of meta-ML research I showed in the beginning, but actually to derive insights about interpretability across model populations and stuff like that.
Yeah.
So to summarize, there are now millions of publicly available models, and we need to chart the model atlas. The model atlas enables all of these tasks, but in practice, the information for most of the models is missing, and we need new methods to learn from model populations, new weights-based learning methods, and we can actually learn from model weights, and models are data points. So yeah, all the papers, the data sets, and the code is available either on my website or on this QR code. And yeah, this work was done with many collaborators. Thanks.
It looks super interesting, Eliahu. Thank you so much. Um,
Thanks.
you know what you mentioned some relation to interpretability and what TensorLeap is doing, and actually, our main focus might be summarized to detecting and solving failure modes of models. So, for example, another layer that we might be able to add is for each model in these subsets, if we get a deep understanding of how it operates, the failure modes it's tending to fail on. And then we might be able to classify failure modes to groups, epistemics kind of failure modes, and
Mhm.
failure modes that related in the model structure, etc. And using the model aspect,
Absolutely.
yeah.
Absolutely. I think it's something that I'm planning to actively pursue during my postdoc, but definitely I think that if companies like TensorLeap start to add more and more information, the information that interests them, because if I jump to the beginning, the case study I showed, which was primarily on the type of fine-tuning models use, right? If we looked at um, this figure, um, I displayed the fine tuning type. This is not really interesting. It's sort of this toy kind of case study, but it'll be much more interesting to see this exact same atlas, but with the failure modes you describe, or all of the insights you have from your work, your research, your use case, your clients, and then I think we can probably start to derive very cool insights, for example, using this type of learning rate results in this, or this cluster of models, this type of whatever does something else. So yeah, one layer is this functionality layer. Here, the colors on the left, these blue ones encode performance, accuracy. So you can imagine instead of encoding accuracy of whatever the MBPP um, benchmark is, if we encode your benchmark, we can already probably find these hidden gems with relation to what you're doing.
Mhm. Interesting. Interesting. Everyone that joined, now it will be a great time to ask questions. So you have the button Q&A in the button. Feel free to prompt us any question you have, and we'll direct it directly to Elio. One question that comes up here is and it's something that we see with a lot of AI teams that working with us today. They already works on AI for a few years, and they have 10, sometimes 100 of models they're maintaining at each given point of time. And many times before they need to deploy to a new operational domain, to a new hospital, to a new road, to a new kind of application, they don't want to retrain from scratch, and they're asking themselves, which model should I take for continued training, for refining, for
Mhm.
fine-tuning on this new domain? Um, is it something that they will be able to use, building their own
A-
model?
Absolutely, absolutely. So I spoke about model discovery briefly and these hidden gems, but when I think about model discovery, I think about four primary types of discovery. So we can think the first type is what is now quite popular. We call it model routing. Basically, if I have a set of models and I have a query, a prompt, give me the best model for this, and maybe also try to minimize, for example, computational effort, right? We know GPT does it. You have the thinking and the fast model, and they route between them automatically. Um, so that's the first type of model discovery, but you can scale it up then to a huge collection of not do it for two models and decide which is better, but for all of Hugging Face, there are 2.5 million models. Try and find the best model for my specific use case. The second type of discovery is what you describe, is basically if I take this huge population, Hugging Face, and I now have my own proprietary data, find me the best. And for example, I know that there is no model that answers my exact use case because it's new data or whatever it is. Find me the best model that I can continue fine tuning from. So that's the second kind of discovery. Then there's a third kind of discovery, which is give me a set of models to merge together or combine in some way in order to get a better model. So now it offers a set of candidates already in order to do it. And there's a fourth one which I currently forget. But yeah.
All right. Interesting. Interesting. It looks great and it looks very comprehensive tool what you guys build there. Will people be able to create their own model atlas on their own model hub, internal models for the companies to get a similar view to?
Um, yeah, so yes. So all of the works I showed, there's this whole set of works over here. Each one of them is tackling a different aspect of constructing the model atlas. Now, if your company has perfect documentation of all of the data, you already go quite far in the process. So if we think of the original atlas I showed, that galaxy or that atlas, then a lot of it is, or most of it is based on the existing information of Hugging Face, but of course that's very partial now. So if you have the documentation, you already went a long way, but you still need to do the representation. So you can
Mhm.
use these methods to construct the logical model atlas, not yet the visualization, just the logical one. And then in the near future, we're hoping to also release tools to construct automatically these nice atlases. You can construct them nowadays fairly easily, these types of visualizations, but they won't be as ordered as the ones I showed initially. So for that, it still requires a manual phase, which we're hoping to automate.
All right. So we'll make sure that we are tracking after your progress. Thank you so much, Eliahu. And everyone, if you have any further question, please feel free to shoot it over to us. We route it to Eliahu and feel free to reach out to Eliahu directly, I guess. If you're curious to hear more about what Eliahu is working on or what Tensorleap is working on where it comes to applied explainability, happy to open a call and run interesting discussions over there. Eliahu, thank you again for joining. Thank you again for leading
Thanks.
the webinar. It was brilliant and super interesting. I learned a lot. Uh,
Thanks.
and see you soon. Okay,
Yeah,
guys.
see you soon. Cheers.